After studying this module, you shall be able to know about ionic strength and activity, understand mean active coefficient and its physical significance, learn different ways to measure activity and mean activity coefficient. We can broadly classify liquid solutions into following types on the basis of degree of dissociation of the solute molecules. Liquid solutions can be of two types: electrolytic, for example KCl solution, ammonia solution, and non-electrolytic, for example glucose solution. The electrolytic solutions can be further classified into strong electrolytes, for example sodium chloride solution, and weak electrolytes, for example acetic acid. In case of non-electrolytic solutions, the predominant intermolecular forces that exist between the components may be due to van der Waals interactions, dipolar interactions, or of the hydrogen bond types. These solutions may be ideal, obeying Raoult's law or Henry's law, and can be non-ideal if the interactions are somewhat stronger. The solutions of electrolytes, especially of strong electrolytes, deviate considerably from ideal behavior. In case of concentrated solution, there exist strong ion-ion interactions and ion-solvent interactions, while in the dilute case, the ion-ion interactions still persist, but ion-solvent interaction play a predominant role. We should note that irrespective of the concentration of the solution, ion-solvent interactions will always exist. In a solution of strong electrolyte, significant electrostatic interactions, which vary inversely as the square of distance between the ions, both between ion-ion and ion-solvent exist. Therefore, these type of solutions deviate from the ideal behavior, and moreover, properties of these electrolytic solutions usually deviates from the laws which are used to derive chemical potential of solutions. Now we shall talk about ionic strength. Ionic strength, abbreviated as capital I, of a solution is a measure of the electrical intensity due to the presence of ions in the solution. It is given as half of the sum of all the terms obtained by multiplying the molality of each ion by the square of its valency. In other words, ionic strength is the cumulative measure of both charge on the ion as well as its concentration in the solution. Mathematically, it is given as ionic strength I is equals to half of summation of Mi into Zi square, where Mi is the molality of ion I and Zi is the charge on ion I. The concept of ionic strength is always applicable to strong electrolytes, for example salts, and it cannot be applied to weak electrolytes. If we consider a solution which has more than one type of ions, then ionic strength can be written as I equals to half into brackets M1 Z1 square plus M2 Z2 square plus M3 Z3 square, this M4 Z4 square, plus so on. For univalent electrolyte of the type example sodium chloride or potassium chloride, the expression for ionic strength will contain only two terms, that is one for cation and other for anion. Hence, we have I equals to half of M plus Z plus square plus M minus Z minus square, where M plus is the molality of cation and M minus is the molality of anion. Z plus and Z minus are the valencies of the cation and anion respectively. While for unibivalent electrolytes of the type Ab2, which dissociate as Ab2 dissociating into A2 plus plus 2B negative, ionic strength I can be given as I equals to half Ma Za square plus twice Mb into Zb square. While for a bivalent trivalent electrolyte of the type A2B3, which dissociates into twice A3 plus plus thrice B2 minus, the ionic strength I will be given as I equals to half 2m3 square plus 3m 2 square equals to half 30m, which is equal to 15 times m, where m is the molality of A2B3 in the solution. The ionic strength lays stress on charges of iron because the charge numbers in the expression of ionic strength occur as their squares. We should note that ionic strength includes contributions from both the number of ions in the solution and the charges on the individual ions. Ionic strength is of a mixture of solution can be exactly determined, but the total concentration of a mixture of solutions cannot be exactly determined. Now we shall talk about non-ideality in solutions. First, we shall talk about activity. The deviation from ideality of a particular solute, and in this case solute is behaving as completely dissociated system, that is, it is behaving as a strong electrolyte, can be expressed in terms of solute activity, which is denoted by letter A. The term activity was introduced by Lewis in 1920s in order to describe deviation in behavior of a gas, liquid or solid state from an idealized pressure state of fugacity. Activity is defined as a measure of the effective concentration of a molecule or ionic species. Activity depends on temperature, pressure and composition of the mixture of the species. Activity of a solute depends on its concentration being proportional to concentration at sufficient dilution. If we plot a graph between activity and concentration, the region of linearity is rather limited, especially for ionic solutes. The standard state is chosen as a hypothetical state which corresponds to the behavior of solute at standard conditions C0 in order to maintain the linear relationship up to that concentration. This is depicted in figure, which is the plot of activity with concentrations. Therefore, in an electrolytic solution, the activity of a solute A is related to concentration M as A equals to gamma into M, where A is equal to activity, gamma is equals to activity coefficient, which is concentration dependent, and M is equal to molality expressed in moles per kg. Gamma or activity coefficient is a correction factor, or we can also say it is a proportionality constant which takes into account the departure from linearity. We should also note here that we have used molality as a unit of concentration because it is independent of temperature. Concentration can be regarded as the number of ions present, while activity can be thought as the availability of the species to take part in chemical reactions and to determine the properties of a particular phase. As concentration approaches zero, activity coefficient approaches to unity, that is, gamma approaches 1. Therefore, activity is equals to molality, that is, it becomes equal to concentration. Again, we should note that in very dilute solutions, since the interactions become insignificant, therefore concentration and effective concentration are the same. Now we shall talk about ionic activity. Ionic activity has more importance in case of ionic solutions or electrolytic solutions than in the case of non-electrolytic solutions. This is due to the presence of strong interactive forces among ions in electrolytic solutions. For an ionic solute of the type AX-BY, which dissociates completely according to the equation AX-BY giving XAZ plus YBZ minus, where X is the number of cations with charge Z plus, Y is the number of anions with charge Z minus. Let nu denote the total number of ions, therefore nu is equal to X plus Y. We also define stoichiometric molalities of each ion based on the analytic molality of the solid electrolyte Mi. M positive is equals to X times M and M negative is equals to Y times M. Absolute activities of cations and anions cannot be determined because activity of a single ion depends on the nature of counter ion to preserve the overall electroneutrality of the solution. For example, in a solution of NaCl or Na2SO4, the activity of Na+ will depend on the nature of the anion, such as chloride or sulfate. Therefore, we define activity of an electrolyte in terms of the ions into which it dissociates. Since positive and negative ions coexist, we define mean ionic quantities. If the activity of the cation and anion is A+ and A- respectively, then the mean activity is given as A ± is equal to A+ raised to power x into A- raised to power y. The symbol of ± refers to mean ionic variable and is defined in terms of number of ions. We also define mean ionic molality M ± as equal to M+ raised to power x into M- raised to power y raised to whole power of 1 upon x plus y. The individual activities of cation A+ can be written as A+ is equal to M+ into gamma+, which is equivalent to x into molality into gamma+. Similarly, for anion, A- can be written as equal to M- into gamma-, which can be further written as y times M into gamma-. Substituting this equation in equation 4, we get A ± is equal to x times M times gamma+ whole raised to power x into y times M times gamma- whole raised to power y, which further can be written as A ± is equals to x raised to power x into y raised to power y into M raised to power x plus y into gamma plus raised to power x into gamma- raised to power y, where M is the molality, gamma plus is the activity coefficient for positive ion, gamma- is the activity coefficient for the negative ion. Now we shall talk about mean activity coefficient. Activity coefficient of individual ions can never be determined because in a strong electrolytic solution, only cations and only anions can never exist. Cations are always accompanied by anions and vice versa. Therefore, gamma plus and gamma- cannot be determined individually. So, we define a new term called as mean activity coefficient, which is represented as gamma plus minus. Mean activity coefficient gamma plus minus is a measure of ion-ion interactions in solution. Mathematically, it is given as gamma plus minus is equal to gamma plus raised to power x into gamma minus raised to power y whole raised to power of 1 upon x plus y. Taking logarithm on both the sides of this equation, we have x plus y times log of gamma plus minus is equal to x times log gamma plus y times log gamma minus. Or this can be written as log of gamma plus minus is equal to 1 upon x plus y into x times log gamma plus y times log gamma minus. Or this can be further written as gamma plus minus raised to power of x plus y is equal to gamma plus raised to power x into gamma minus raised to power y. In this equation, the value of x and y depends on the nature of the electrolyte. Using equation 9 in equation 7, we get A is equals to x raised to power x into y raised to power y into m raised to power x plus y into gamma plus minus raised to power x plus y. Or we can write A as equal to x to the power x, y to the power y, m gamma plus minus whole raised to power x plus y. Debye and Huckel suggested a theory to find out the mean activity coefficient gamma plus minus in order to measure the ion-ion interactions present in the solution. This theory is applicable only to strong electrolytes, for example to salts. These types of solutions are electrically neutral and they dissociate completely. Example can be taken of sodium chloride. For ideal solutions, mean activity coefficient gamma plus minus approaches 1 as m, that is molality, approaches 0. Also, for even low concentration solutions, gamma plus minus value deviates from 1. Experimental plot for variation of gamma plus minus with square root of ionic strength is shown in figure. The variation depends on the nature of electrolytes. Figure represents the graph showing variation of gamma plus minus with square root of ionic strength. Debye and Huckel theory ultimately accounted for variation of mean activity coefficient with square root of ionic strength. Therefore, using Debye-Huckel theory, we find gamma plus and gamma minus theoretically. For different types of electrolytes, the activity can be calculated as follows. For example, for uni-univalent electrolyte of the type AB, which dissociates into A positive plus B negative, X is equals to 1, Y is equals to 1. Therefore, A, which is equal to X to the power X, Y to the power Y, m gamma plus minus to the power x plus y will be equal to A is equals to 1 to power 1, 1 to power 1 into m gamma plus minus to power 2, which becomes m square into gamma plus minus square. Examples are sodium chloride NaCl and copper sulfate CuSO4. For the uni-bivalent electrolyte of the type Ab2, which dissociates into A2 plus 2B minus, x is equals to 1, y is equals to 2. Therefore, A can be written as 1 to the power 1 into 2 to power 2 into m gamma plus minus to the power 3, which gives us A is equal to 4 times m cube into gamma plus minus cube. Example of barium chloride BaCl2. For electrolyte of the type Ab3, which dissociates into A3 plus 3B minus, x is equal to 1 here and y is equals to 3. Therefore, A will be equal to 1 to the power 1 multiplied by 3 to the power 3 multiplied by m gamma plus minus to the power 4, which gives us A is equal to 27 times m to the power 4 into gamma plus minus to the power 4. Example is of ferric chloride FeCl3. For the electrolyte of type A2B3, which dissociates into twice A3 plus thrice B2 minus, x is equal to 2 and y is equal to 3. Therefore, A will be equal to 2 to the power 2 into 3 to the power 3 into m gamma plus minus to the power 5, which gives A as equal to 108 multiplied by m to the power 5 multiplied by gamma plus minus to the power 5. Example is of Fe2Cl3. Now, we shall talk about the measurement of activity. For volatile species, activity can be measured from its equilibrium partial vapor pressure. For non-volatile components such as sodium chloride NaCl or barium chloride BaCl2, we do not measure activity from the partial vapor pressure because they do not have measurable vapor pressure at most of the temperatures. We therefore use a different approach, that is the vapor pressure of the solvent is measured, and using Gibbs-Duhem relation, the change in the solvent vapor pressure is translated with concentration into activities for solute in the solution. The activity A of an electrolyte is a property that can be measured by experiment. Example, by measuring colligative properties such as osmotic pressure or freezing point depression of the solution. We can determine the mean ionic activity coefficient gamma plus minus of ions in solution using Debye-Huckel equation or from the solubility product or from electrochemical methods using Nernst equation. Now I shall summarize. In this module we have learned electrolytic solutions deviate from ideality due to the presence of significant electrostatic interactions. In order to account for deviation from ideality of solutes, Lewis introduced a term activity which is represented as activity is equal to gamma multiplied by molality, where gamma is the activity coefficient. Due to interactions between the component ions in solutions, they deviate from their ideal state. The factor which influences this interaction is the charge on a particular ion, and therefore useful function in this context is ionic strength, abbreviated as I. I is equal to half summation MiZi square. In order to maintain electroneutrality in solution, cations and anions exist simultaneously, that is, positive and negative ions coexist. Therefore, we define mean ionic quantities for such solutions. Mean ionic activity A plus minus is equals to A plus raised to power x multiplied by A minus raised to power y. Mean ionic molality M plus minus is equals to M plus raised to power x into M minus raised to power y whole raised to power 1 upon x plus y. Mean ionic activity coefficient gamma plus minus is equal to gamma plus to the power x into gamma minus to the power y whole raised to power 1 upon x plus y. We measure activity through experiments such as by measuring colligative properties, which include osmotic pressure, depression in freezing point, etc.